This is one of our webinars we're going to do. This one has to do with the rotating region setup in FloEFD. We did one last week for transient analysis setup, which I'll probably do again in a couple of weeks. You know, we may redo a couple of these just to give more people an opportunity. So the rotating region setup in EFD is it's pretty straightforward, but I'll go through a couple of guidelines, some specific ideas here. You know, first, the rotating feature activation. What is the rotating region component? You know, how do we create that? What it actually is in the assembly. The definition of the rotating region condition in EFD, it's a condition just like any other boundary condition and how it's applied. The stationary wall conditions, which has to do with any stationary walls or objects that the rotating region intersects with, and we'll see what that means. You know, so basically there's a way to handle those wall conditions. Different types of regions or shapes of a rotating region. Again, some guidelines, real simple, some pictures I have here in the presentation. And then some meshing guidelines. So I have a few slides here. We'll step through this, and then we'll go into an actual example using the rotating region setup in EFD, something that everybody has access to as long as you have EFD installed. So our rotating region is going to be worked with this example model that we already have as one of our tutorials. It's called the tutorial C6, the CPU cooler. Everyone that has FloEFD installed has access to all of the tutorials. This is just one of them. And the tutorials are always included in the installation folder of EFD. Obviously, your version number and your version, CAD version will be a little different, okay, if it's FEX for NX or FES for Solid Edge, okay? And the number will be different. But the installation folder for the last few versions, 17, 18, 19, should all be in the same similar path, okay? And not only do you have access to the examples themselves, the model examples, but you also have access to a tutorial PDF that you can use to follow through and step through the example tutorial, okay? The PDF file is accessible from the Start menu items under your FloEFD folder item, okay, just tutorial PDF. It is a PDF file in the installation folders as well. You can search for it. It's not the same folder as the example model, but it's one of the installation folders, okay? Just do a search for it and you'll find it. It's in an English language folder, something to that extent, okay? So we're going to work with this as our example model when the time comes. And you can do the same thing later on. You can use the same model for reference or practice on it or take it and use some of the ideas for your own model afterwards. So the rotating region, the function and activation. So the rotating region allows the user to specify a local rotating frame of reference and analyze the fluid flow through the rotating components of the model, such as a fan or impeller or a pump, okay? The rotating feature is activated in general settings of EFD, which is something you're always going to step through that, whether it's through the wizard or you adjust it in the model settings itself. And when you do this, you also want to check for your project units to set it up for your desired angular velocity unit setting. Again, we'll see this as I go through the example. Very straightforward, something you're going to do all the time anyway. It's just a regular process. In EFD, there are three ways of defining the rotating feature. They are the global type, the local with averaging, or local with sliding technique, okay? And I'll go through each one right now in the next slide here, okay? So the three types of rotating region in EFD. The global type, that basically means the entire model and the global coordinate system are considered as rotating with the specified angular velocity. So there is an example for this as well in the tutorials. It's an earlier one. I think it's called impeller. Okay, it's like A5 or maybe B4 or something like that. So it's called impeller. And it's just a model of an impeller. Okay? In that case, you can basically say the entire model is rotating. Okay? It's not local to a specific part or region. So it's a global rotating part or global rotating model, and everything is meant to rotate. Okay? It's applicable when all non-rotating components are axisymmetric with respect to the selected rotation axis. Again, the entire model rotates. It's very rare that you're going to use this for anything because more often than not, your model has a fan or impeller within a local region of an assembly. Okay? In that case, that comes down to the second type here, which is local with averaging, which is typical of a steady state analysis. So I would say 70 to 80% of the time, your rotating region type is going to be local with averaging, okay? These are cases where the rotor-stator interaction is weak, okay? So basically you have a free flowing fan or pump in some sort of electronics enclosure or some sort of pump assembly. And the flow parameters are averaged on the rotating region bounds. So what that means is on the interface between the rotating region and the non-rotating or stationary region, that bounds or that radial circumference, the flow parameters there are averaged, okay? Again, it's a steady state analysis, so it's not very, computer intensive, and it's easy to set up, and, you let EFD do the rest of it from there on. And again, this is 75 to 80% of your projects will be local with averaging. The third case, which is a newer case that was added a couple of versions ago, is local with sliding technique. And this has to be run as a transient analysis. Okay, this is where this represents cases where the rotor-stator interaction is strong. Most of the time we use local with sliding technique. You can use it in any case. You could use it for any fan or pump or impeller case, but more often than not, these are cases where it's a radial type fan or a blower type fan in a blower assembly, like in a volute, okay? What that means is away from that impeller, away from that radial fan, the model is not very axisymmetric, okay? So that means it's more, it lends itself better to be more of a transient analysis using this sliding technique. The cells in the rotor-stator zones are connected via sliding interface, so there's more information going on between that interface of rotating versus non-rotating. And being that it's a transient analysis, that interface literally is being moved almost or adjusted every time there's a time step, so that way there's a connection between when it's adjusted to where its original position was. And that sliding interface takes more computation. Obviously, it's more computation intensive, okay? The flow field is unsteady and allows for a more accurate solution. The downside of this is it's computationally more demanding. It will take longer to run. You have to set up a time step, okay? You should probably account for more cells as well. In other words, we have certain guidelines for the rotating region in general, but when you get to the local with sliding technique, those guidelines are even more aggressive. So you probably will need more cells in the local region of the rotating region, plus in the area of any gaps and offset from the fan region or impeller region. Okay, so it's more cells, more CPU time overall, more calculation time. Okay, but we do use this again, more popular for blower motors, things like that. Things that are not as axisymmetric and not as free-flowing, to the open stream as a typical fan or pump. So the rotating region, the component and definition. When we refer to a rotating region, we basically mean we need to create an actual solid component in the model assembly, usually as a new part within an assembly. And that new part has to encompass or enclose the rotating part, being the fan or impeller, completely. Okay, so whatever you create as a rotating region has to encompass the fan entirely. Obviously a little larger on all sides, and there are some guidelines there too, and we'll see some pictures and some examples. The rotating region must be axisymmetric with respect to the rotating component's rotation axis. That just makes sense. Obviously, whatever you have as a fan or impeller, whatever the rotating region is going to be created as, it should be more often than not a 2D sketch that's rotated in the 360 and encompasses that fan, like a disc, basically a hockey puck or a disc. That's the most simplest way of describing it, okay? The new solid part must be disabled, hence making the part a dummy region, which is invisible to the flow. This happens automatically in EFD, and I'll show you, when that happens. But the idea here is EFD has a feature called component control. And in component control, EFD allows the user to make a part invisible to the flow by disabling it. When we disable something in EFD, we can almost call that part a dummy part now. It's still a solid part in the CAD, but as far as EFD is concerned, it's invisible to the flow, so it has no effect on the flow. But at the same time, that volume, the dummy region or the dummy part, the volume of that part can be used for something like this. It can be used for letting EFD know that the cells that fall within that volume are being solved for in a rotating reference frame. Okay, that's how it knows which cells are being applied this rotating reference frame. That dummy region, that disabled part, we do this all the time in EFD. That can also be used for heat sources. It can be used for a local mesh region, for volume parameters or volume goals, surface goals. So there's more than one reason to use that dummy region in EFD, that disabled feature. Okay, and I'll show that as well when we get into the example. The rotation axis and direction determined with a right-hand rule, opposite direction defined by negative RPM. So what that means is once we're ready to define that rotating region object, the definition in EFD, EFD will give us, indicate by an arrow the direction of rotation, just by using the right-hand rule. So by seeing the arrow show up on the screen, we'll know which way is positive versus negative and versus counterclockwise and clockwise, okay? That'll tell us what direction we need to rotate or what direction that fan should be rotating. The flow characteristics within the fluid cells, which are enclosed within the volume of the dummy region, will be solved within a rotating frame of reference. Again, that dummy region is what controls or how EFD knows to calculate those cells using a rotating frame of reference. So examples of a rotating region or what EFD can handle in a rotating region, this is just some pictures of types of pumps and fans that can be simulated, whether they are centrifugal or axial pumps or blower units, blower models, fans, propellers, impellers, okay, turbines. These are all types of pumps that can be simulated using a rotating region in EFD, okay? It's a broad range. You can use it for almost anything here. You don't have to. It's just a more detailed way other than, you know, applying a typical fan curve to an annulus. So obviously, it's one step better than that, okay, with meshing, explicitly modeling the part. So the rotating region and stationary walls. Any intersection of the rotating region with other fluid and solid regions must be axisymmetric, which is typical of a fan housing or a pump housing, okay? So typically when you have that fan impeller or the fan itself, it's sitting within a solid housing, a cylinder, let's say, okay? So our rotating region would be this orange or red colored outline. And by the, you know, just the most general way of making this, again, is just a rotated 2D sketch to make this hockey puck or disc. And ideally, we would probably recommend, well, the best way to do this is to make sure that the rotating region encompasses the fan itself and keeps itself within the fluid region only. What that means is ideally you would like to break that interface or create that interface in the fluid region, so on both sides of this interface you have fluid cells. So there's a fluid gap from the fan to the interface, and there's another fluid gap from the interface to the solid, to the inner wall, okay? That's ideal. But in some cases, it may not be the best. It may not work the best for the calculations, or it may not be economical, okay? So in most cases, placing the rotating region within a solid body instead of ending the interface within a narrow gap between the rotating component and non-rotating model is recommended. So what that means is if this gap is too small to cut in half, to break, it's okay to take that rotating region and drop it into the solid, end it into the solid, okay? The reason why this is allowed is, number one, we may want to avoid this narrow gap because if we go to our next, when we get into the slide about the meshing, one of the things that we typically recommend here is between the tip of the fan blade and the interface, we recommend at least 2 to 3 cells. And that would be the same on the other side of the interface to the solid. So I usually go by 4 cells. I would say you want at least 4 cells between each interface, okay? That would mean in this very small gap, we need to put 8 cells to really calculate this reasonably, okay? And that means 8 cells in the entire height and in the entire 360. And that may not be economical. That may lead to 10 million cells just in this area. And it's just not, it's a lot more than we need to put here, okay? So to avoid that, you know, 8 cell minimum, let's say, we can do this. We can take that rotating region, drop it into the solid. Now, everything in here that is fluid is represented as a rotating reference frame cell, okay? And we're not as concerned with the gap being as small. In other words, we're only in a fluid gap, and it's all rotating. So having 4 cells across this gap is okay now. We don't need 8 cells. So that'll cut down the number of cells in half right there, okay? And again, that's in the entire 360. The non-rotating geometry is easily accounted for by applying a stator wall condition to any surfaces where it's overlapped. And what that means is, well, now that we've overlapped this rotating region into a solid, that's basically saying that the fluid cells that touch the solid on the entire inner cylinder surface, those fluid cells are being solved for as they are rotating, as though they are rotating, which means that's telling the EFD that the wall is also rotating, and that's not the case. So to account for that, all we need to do is apply a stator wall condition on this inner surface for the entire 360. And that will counteract the effects of the cells being in the rotating reference frame. So those surface cells, or those, I should say, the surface of that wall will not be rotating in effect. It's going to be stationary. And this is how we do it. And I'll get into the example when we do this to show you how to apply that. So it's a very simple counteract. It's a very simple way to avoid having those cells moving. Now, if you forget to put those walls into a stator wall condition, it's not a big deal. You can still run the analysis, but you'll know right away that something's not right, because once you make a couple of surface plots or, cut plots, you will see moving wall effects on these surfaces, and it should flag you right away to say something's not right. I shouldn't see those walls in a moving condition or with effects of a moving wall. Okay, so you'll notice that it's very obvious once you get to run this, and you'll see effects of that happening that shouldn't be happening. So that'll tell you I forgot to put the stator wall condition. Okay. So here are some images of examples for rotating region shapes. Okay, again, typical shape is a revolved 2D sketch that encompasses the fan or impeller. Okay, this is okay. Something like this is okay. It can be a little larger in the upper and lower region. Even better would be a little larger in the radial direction. That is always recommended if you can do that. Again, unless you're breaking something in half, you're breaking that interface, that gap, but you don't want to make it a very small gap. But this is always giving it more fluid interaction. Here is better because you're giving the flow some space to come off of the effects of the fan. Okay, basically some space to extend itself. Okay, for extension. So that's always good there. There's always something, reason for that. Something like this, there's no reason to make a shape here. There's no reason for that. It's just not necessary, and it may cause more issues than it's worth. Okay, so no reason to make it detailed to this effect or add a shape that's not there. It just doesn't make sense. It's not reasonable. Some other ideas: if the fan has a hub or some sort of center cap, then okay, you can make the entire rotating region a little larger. That's okay. It just means that all of the fluid cells in this region are in a rotating frame of reference. Again, I would probably do something like this where it's stepped. This is even better, okay? Just make a step, a 2D sketch with the step, and then revolve that. It's just very simple. You could actually, adjust to the shape of that cone if you wanted to. It's not necessary, or even make the curved cone, okay, almost follow. But that's even being too precise. I still wouldn't even do that. I would still go to something like this. Keep it as simple as possible. This is the best way to do it. Okay, it's just simpler. It's easier, and I think the calculations have an easier time, simulating this than trying to adjust for what's rotating versus non-rotating here. Okay, just keep it real simple. It just makes more sense. Some shapes that just don't make sense at all, or you should avoid doing something like this, is cutting the fan in half. I don't know why you would do that. Making it smaller than the fan in the radial or the axial direction. Why you would do that? Again, I'm not sure. And not being aligned with the fan object. Again, that doesn't make sense at all. If the fan itself is not aligned with respect to the global system, then it might be a good idea to rotate the model so that everything is aligned, or at least the fan may be. It just makes more sense if you can do that. If not, then just make sure the rotating part, aligns itself with the fan part. Okay. Again, this just doesn't make sense. It may run, but I just can't imagine the results would make sense here. Again, some other shapes that just for sake of avoiding it, why put this detail into the rotating region? I wouldn't do that. There's just no reason for it, okay? Make it simple. There's no reason to make it this complex or convoluted. It just doesn't make sense. And I think EFD just wouldn't like it either. It just would give you bad results, okay? So again, avoid some of these things, just typical, you know, what makes sense of that rotating region for your case. In the outward or radial direction here, again, you want to encompass the entire fan, the fan blades and the fan diameter. If you have to be this close to the fan blades, that's okay. Just remember, you know, the guidelines say that we should have at least 2 to 3. I try to put 4 cells here. So again, that's going to be pretty small cells, okay? But if you can extend it a little bit and add more fluid, you know, give it some space to expand, definitely go with something like this. Now your 4 cells across are much easier to achieve. In other words, you don't have to do, you know, 6 or 7 levels of refinement. Maybe you can do this in 2 levels of refinement. Okay, it's going to save a lot of cells. So this is much more desirable. But in some cases, you may not have a choice. It depends on the model. Every model is a little unique. Okay. Some meshing guidelines for the rotating region. Use the rotating region itself for a local mesh. So basically, just because we used it for a rotating region doesn't mean we can't access it or use the volume and apply a local mesh in there as well. That's just another reason why we have it as a disabled body, okay? It's recommended to have 2 to 3 cells across the gap between rotating boundary and the surface of the rotating component, okay? So again, in that gap, you want at least 2 to 3. I try to put 4, but 2 to 3 will work. It may be a little coarse, but it will still work. Again, here, this is good. This is a good representation of the mesh where we're doing some local refinement. This one's even better, okay? Obviously, it's refined to one more level than the previous one, and I would probably make it more uniform across the blade. So in other words, you can kind of see here the level of refinement changes. So I would almost grab the end of the blade and make it more uniform in that region at the outer perimeter, okay? That, just make it more uniform. It's cleaner. And it just works better when the cells are more uniform, especially coming off of the tips of the blades, okay? In both cases, typically we also try to achieve 4 cells. Again, 2 to 3, but 4 is good across the space between each blade. That's a common thing. And more often than not, that's going to happen anyway, because obviously as you get to the higher refinement, you have at least 4 or 5, maybe even 6 cells across, okay? So that's a common thing you're going to get almost anyway. You're never going to run something this coarse. That would just be too coarse. It would run, again, it would run in EFD, but your answers are probably not going to be very accurate. This is okay. This is even better. Again, the second level of refinement here. As we move away, the meshing, as we move away from that rotating region, allow for a smoother gradient in the cell refinement from the rotating region to the main flow stream. Again, it just makes for better calculation. It lets the flow expand better into the main flow stream. Again, the coarse mesh is okay, but one more level of refinement is even better. Okay, you know, don't be afraid to add some cells. Again, you know, unless you're adding 10 million cells, then obviously I would say don't do that. But if you're adding, you know, 100,000 cells, then why not? You know, you may as well do it. You know, get even better, more accurate answers for your mass flow rates and your pressures. Okay. And okay, so the contact. So again, if you have any questions when we're all done with this, you can ask questions at the end. You can always email me tomorrow, later on, next week. You can also submit a service request online at our support center, okay? Again, and we can do this through a WebEx on your model or something specific in one of your examples. Okay, so I'm going to go to my model. Any questions on the presentation so far? Otherwise, again, you can always ask while I'm working in the model itself. Okay, so this is our typical tutorial model, the CPU cooler. Okay, it's comprised of a few parts here: a heat sink, a CPU, a socket, the retention clip, and the housing for the fan item itself. Okay, a PCB board. And there's a core here, a copper core as well. So this is already pre-made. I opened it up as the tutorial, okay? So I just opened it up. It has the settings in there, but I'm going to go through it as though the rotating region is not applied yet. Okay, so I've set it up. I've gone through my wizard. the model itself is here, but I have to set it up for the rotating region. And here's obviously my explicit fan that we're going to model with mesh in EFD. Okay, so first thing we need to do is go to our general settings. And in our general settings, when we step through the wizard or we adjust this on the, during the model, one of the things I need to apply here is my rotation feature. That's our first application. Okay, that's the item we need to turn on here so we can apply that rotating region. And once we activate that rotation feature, we now have our pull-down menu for the three choices here: global, local region sliding, or local averaging. Okay, again, the averaging is the steady state, the more typical, the more common way of doing this. The sliding is the transient. We're going to stick with the averaging right now. Again, for this model, it doesn't need to do a transient here, and we're going to apply that and say okay. And we're doing this as an external, just so everybody realizes it's an external model, where the domain is basically sitting on this PCB, and I'll show that later on as well, just to make sure you see that. Okay, so here's our domain, okay, basically sitting on that PCB as an external. One of the things that you may notice as well, the domain is not necessarily on the PCB itself, but it's embedded to the PCB, and it's a little smaller. Again, that's just another guideline for an external analysis where you're trying to simulate something on a PCB or on a table, okay? Just make sure that that the external domain is embedded into the solid. It's not sitting on top, it's not at the edge, and it's not at the bottom. This is another guideline just in general for external analysis, okay? Something that we try to keep in mind here. Okay, so we have our item here. Now, if I need to create my rotating region, obviously you're going to do it in your CAD system, whatever it may be. Obviously, every CAD system has their own way of creating new parts or new objects. And so how you do that, it's up to you. I'm going to create a simple part here to be part of my rotating region as an example. So I'm going to insert a new component. I'm going to build it on my front plane here, and the first thing I need to do is create a center line axis to where I need to rotate this sketch that I'm going to create. So there's my center line, and then I'm going to create a simple 2D sketch. Okay, so there's my 2D sketch with my center line, and I'm going to revolve that in 360. There's my 360, say okay. Okay, and I've just built my rotating region part. Simply said, it's a 2D sketch revolved into 360. It's a hockey puck, basically, with no real shape to it. It encompasses the entire fan and a little bit more. But again, very simple. I did it really quick just to show you that, as far as making the steps in there, I could be more precise, and I'm going to do that. I'll show that anyway. But this is a simple rotating region part, okay? So I'm going to suppress that just out of, I don't need it right now, but I'll rebuild my model here, and I'll just suppress that because that's the one. And we're going to go to the, we're going to go to the one that was actually created here in the tutorial. It's already here, and that's the tutorial part, okay? That's the rotating region that was built for this model, okay? So you'll see it's a little bit more precise. In other words, it has some steps in it. Just like I explained before, again, ideally we would want to break this interface in half, this region of the fan blade tip to the surface, but then that's going to pose an issue where we need to put 8 cells across this gap, and I don't want to do that, okay? So for that reason, they created the rotating region a little larger, and they purposely embedded it into the solid of the attachment clip here, okay? So it embeds into the solid, and then in the horizontal position, it's in the fluid break just between the heatsink and the fan blades, and then it embeds itself again into the solid of that fan attachment, the hub, okay? That's the 2D sketch that was revolved. This is what comes out of our rotating region part. That's the part we use, okay? Very easy to do. It's just a few steps. It's a little larger in all the directions, and it's embedded itself into the solid, which is we're going to take care of as well later on. Okay, so now that we have our rotating region part defined, it's part of our model. I'm going to make that transparent so we don't have to see it completely. And I'm going to define it now as a rotating region in EFD. So once we have the rotation feature activated, either from our input data tree, we should have rotating regions available here, or from our conditions, we can go to our pull-down menu and say rotating region. I'm going to insert a rotating region now in the model. And the first thing that comes up, obviously, is our prompt box. It's looking for a component to apply the rotating region. And obviously, our component here is that solid that we just created, okay? As soon as I click on that solid and select it, it throws itself into the prompt box, but it also shows us our right-hand rule indicator, okay, our arrow. With the thumb direction is down, and then the rotating direction in the positive shows us the direction of our fingers in the right-hand rule, okay? So this is telling us that positive direction rotation is clockwise, okay, so with the positive value. And then it's also looking for our angular velocity in radians per second. Well, I don't have it in radians per second. I have 4,400 RPM. That's what I need to apply here, and I don't want to convert it. So let's change that. Let's go to our unit settings here because we can do that on the fly. Let's go to our project units, look for our loads in motion, angular velocity, and let's change that to RPM. That just makes more sense. Okay, RPM, say okay. Now let's go back and insert that rotating region again. Okay, let's click on the part. Okay, now we're in RPM. Okay, now if I need to apply a positive RPM, then it would be clockwise here. But I want this fan should be rotating in a clockwise direction. So that means I need to enter a negative RPM. Oops, 4,400. Okay, and as soon as I do that, you can see that the rotating arrow turns to the other direction, telling us that that's the negative direction. So that means counterclockwise is negative. That's the way I need this fan to simulate, to rotate as though it's in the negative direction. Okay? 4,400 RPM. The other thing that shows up here, which is on by default and you don't have access to it, is the checkbox for disable solid components. So EFD is going to automatically disable this part because even though it's a solid part in the CAD, we don't want it to be solid in our simulation. We need it to be invisible to the flow. Okay? So that happens automatically. And other than that, I mean, this setup part of it's done. I can say okay. Now, how do we know if that part is really disabled or not? Well, that can be done in our component control. It's always available regardless of what the part is. So if I go to my component control, this shows me a list of my assembly with the parts, and my rotating region part, which is right here, highlighted there, is unchecked. The fact that that part is unchecked tells me it is disabled, which happened in my region definition automatically. EFD did it for me. But if I needed to do it manually, this is where I would do it, okay, and hit apply. So it's already been done for me. We know that. That's been done automatically. Okay, so we set up our rotating region. I'll hit the save button here. And we have to go through one more process here before we do this, before we actually allowed to run it. When we made that rotating region, or when it was made for us, remember I mentioned earlier about the stator walls, about the fact that this rotating region is overlaying or overlapped into the solid. And we know that those solid surfaces of this clip, of this attachment, are not rotating. They shouldn't be rotating. They should be stationary. So how do we account for that? Well, all we need to do is apply a wall condition to those surfaces. So sometimes the hardest thing to do is, well, how do we select those surfaces? That's probably the hardest thing, just getting to those surfaces and selecting them. Okay, I usually hide some of the parts. You can put it in section mode, whatever works better. Okay, but one way or another, you have to get to those surfaces. And what we're going to do is we're going to introduce or insert a boundary condition. And in our boundary condition definition, we have three types that we can use in EFD. A flow opening, a pressure opening, or a wall condition. I'm going to define a wall condition for the surfaces that I'm going to select. And not only is it a real wall, but underneath the box for the type, there's a checkbox for stator. And that's going to tell EFD that the walls I select now, the surfaces I select, are stationary walls. Even though they fall within the rotating region definition, the bounds, they are stationary walls. So it's going to counteract the effects of the rotating reference frame. And now I just have to basically, from my prompt box, I have to select the faces that are all part of this stationary, where the region overlaps. Now, these surfaces are obviously larger because we know that region really only overlaps in a circular mode here, in that shape, but that's okay. The fact that the surfaces are larger doesn't really mean anything. It's redundant. We already know they're stationary. But it's important to make sure I collect all of the surfaces that really do fall within that rotating region. Okay, so there's about 10 of them here, I think. I think there's one more. Oh, somebody's got their video. Okay, so I think I selected them. I selected all of the available ones, okay? So these 10 surfaces, even though they fall within that region, the rotating region, they do not act as rotating. They are stationary. Now, if I wanted to select more surfaces, I could. It's just redundant. I don't have to, but I could go in and select more surfaces if I wasn't sure. And that's okay. There's nothing wrong with that. It's redundant. Just because they're already they don't fall into that region doesn't mean it's going to make any difference. It's not going to make any harm, okay? So I could select more surfaces, but there's no reason to. So those I know for a fact fall into that. I'll say okay. Oop. I probably selected too many surfaces there. Okay, I probably selected surfaces that I didn't need, and that's why I complained. So if you need to remove surfaces from here, just highlight the surface, right-click, and say Clear Selection. Or you can do all. I selected all of them. I should have just done. Oops. Let me go back and get these in here. This one, this one, and these three here, I think it was. Okay, let's see if these complains about these or not. Oh, something, it doesn't like something here. Okay, so those are the surfaces. There's coming up with one of the surfaces it doesn't like, but that's okay. I could fix that later. Okay, so we did our surfaces. We have our rotating region defined. And then there are some goals here, okay? And I'm going to activate my first project because this is the one that I ran and this one works. Everything's already applied. Here's my real wall surfaces. And here's my rotating region. We already know that. It's just hidden here. Okay, I'll unhide that. Show my heat sink. Show my fan. And show the rotating region. Okay, so we have everything set up in this model. Now, another thing that we're doing here. So we have some goals here that we applied for the setup. And a couple of the goals that we have here, the more important ones are point goal. There's a point goal at the top of that CPU, at the top of the chip for max temperature solid. And there's even a surface goal at the top of that chip for max temperature solid, okay, surface goal. So we applied those goals. Those are important to the analysis. But a couple of other goals that we can apply, which just help in, let's say, convergence and monitoring and seeing how the mass balance flows here, okay? So one of the things that they did with the shape of this, there was a reason for this, and I mentioned this before. So they embedded the solid of that rotating region into the surrounding clip. And another reason why they did this, which you can do on your own, in your own model, and there's ways of doing this so that way you can make use of this later, you'll notice something here. All of the flow that enters the fan has to go through the outer perimeter and the top surface. So all of the flow that enters the fan is limited by these two surfaces, okay? Because they end in the solid, it gives us a definitive break. So that can be a goal for mass flow. If I use this top selection and the outer perimeter surface, those two surfaces can be our mass flow rate of flow entering the fan, okay? It's a definitive location, okay? On the other side of that, the bottom face of the fan, I should say the bottom face of the region is locked between the outer surface and the inner hub surface, the attachment, which means that annulus, there's an annulus there, that annulus can be another surface goal for mass flow rate exiting the fan. So all of the flow that exits the fan has to go through that surface. So now I have a specific goal for mass flow rate entering the fan, mass flow rate exiting the fan, and I can use those two as an equation goal for mass balance through the fan, Okay, just another thing to use for monitoring, to make sure things look correct, that they're working well. If these two values are not the same, other than the direction, one will be positive, one will be negative for flow coming in and flow going out. If those two values are not the same, that's telling me something's not right. I either have a leak somewhere, or I didn't select the correct surfaces, or they're not really locked in between solids, okay? So there's a reason for doing it that way, for making that shape. It lends us to make these goals, and then the equation goal as well, okay? So again, it's just another step to do. It helps, you know, monitor this, and again, for other purposes, when you get later on down the line, you make 2 or 3 versions of this, you always have those goals there, okay? The only other thing that I may do here that I would probably do in my own model, not as the test model is very simple, but I may use that rotating region as a local mesh. So I can select that rotating region, insert it as a local mesh, and since the region is already disabled, it's invisible, I can act on the cells in that volume, just like the rotating reference frame is acting on the cells, okay? So if I want my fluid cells in that region to be 2 levels of refinement more than the base mesh, I can adjust it here. If I want the cells that are attached to the fan blades, which are the interface cells, the fluid-solid interface cells, those would be the bottom refinement level here, and I can make those 3 levels of refinement, okay? Now, usually when you're doing the meshing, and this could be a whole other webinar, you want to do, you know, run the mesh, take a look at it, you know, investigate, is it reasonable enough? But you may do this a couple of times to get a reasonable mesh, something that falls into the guidelines of having 3 cells or 4 cells across, you know, the blades, 4 cells across the gap, things like that, okay? But that could be one of my local mesh items. I could even have another, you know, I could apply another local mesh just on the outer perimeter where I force the cells there, the fluid cells, to be another level of refinement higher, okay? Or I could add another part and disable it, even go one step further, okay? All of that's going to be part of your process of setting this up to get reasonable results and more accurate results, okay? So that's all set up. It's ready to run. I'm not going to run this. I did already, but it ran. Here's my solver window. I have my preview plots showing me my temperature distribution, my velocity magnitude distribution through the fan, through the region, and downward over the heat sink. Here is the goal plots showing me my mass flow rate of the top goal versus bottom goal, flow in versus flow out, which obviously they should be very close, and the equation goal should be 0, okay? And here's the goals. They're overlaid. The point goal and the max temperature of the surface, 325 and 329 degrees K for the chip, okay? So this is my solver window. I've run the model. It looks good, reasonable results. When I get back to my window here and the results have been loaded, obviously I can show my results here. Okay, let's hide the geometry and do a quick plot of the temperature distribution showing with velocity vectors overlaid. Okay, typical plot, something you would show here. Another way of showing this is using streamlines. Okay, this is a temperature contours with streamlines applied, evenly spaced streamlines. Okay, again, just something typical to show in this type of plot. And I have another plot here, which is, oops, this one is, there you go. This is velocity magnitude with velocity vectors overlaid. Okay, all part of your cut plots, your typical cut plots. Again, you can see the outline of the rotating region. Flow acts as though it goes right through it. Okay, it's invisible to the flow, but we do know that the cells that fall within this region are being solved for in a rotating reference frame relative to the static reference frame around it, surrounding it. Okay, but the idea is you can still see that interface because it is a part. It's a part in the model. Okay, so you will see that. Okay, that's all part of the post-processing. Nothing really changes. Nothing's different than that. I also have, let's see, I think I have a surface plot here showing the velocity on the surface of the fan blades. Okay, so there's a surface plot on the fan blades showing the velocities on the surfaces, okay, of the fan blades and the hub. Again, this is all part of your post-processing, something that you would typically do anyway, but now you have a rotation region definition in here with the effects of the fan rotating. Okay? Goal plot, again, something you're going to do anyway. We can show it down here, all of our goals. We have our goal plot table, and then we have our history of our goals, just like we would in our solver window. Velocity, average velocity, global goal, temperature solids, and then our mass flow rate in, our mass flow rate out, and our equation goal. Okay, this is a typical post-processing, just happens to be that we have our rotating feature in this model. Okay? All right, so any questions? Any questions on the setup? Obviously getting the meshing down. You know, the meshing is going to take a couple of trials. There's nothing, you know, you're not going to be perfect the first time, but you want to definitely get some reasonable mesh in there and then just apply everything.